let us look at the rates of frame indifferent vector. Let V be a frame indifferent vector. Not to be confused with the velocity. Velocity is not frame indifferent, and this is just a ordinary frame indifferent vector for which we know vectorially V plus is equal to V. Both the observers see the same vector, but the components are different. So one observer sees VA plus EA plus, and the other observer sees VI EI. Whereas VA plus is related to VI through this transformation relation. Now, let us define something called an in-frame rate of change. In-frame rate is for the O observer, who is sitting in a fixed coordinate system. The in-frame rate is the rate that he sees while being fixed to the coordinate system. So that in-frame rate, which we denote by this symbol, in-frame rate of V would be simply VI dot EI. And in-frame rate of V plus would be VA plus dot EA plus. So this would be the in-frame rates. So if the vector itself is frame indifferent, how are these in-frame rates related? So let us start with this equation. So in-frame rate of V plus is equal to, use this QAI VI dot plus QAI dot VI EA plus, and then you can so QAI EA plus is EI, so the first term is VI dot EI, and the second term is this can be replaced by omega AB QBI VI EA plus, and this remains as VI dot EI, and this is QBI VI are components of VB plus. So this is omega AB VB plus EA plus, which is omega times V. This is the in-frame rate in the O system. So this is delta V. So we have this equation between the in-frame rates. So the in-frame rates are not frame indifferent, though the vector itself is frame indifferent. Now, what we can now use is, we can use the fact that V plus is equal to V, and this quantity we have already proved is W plus minus W. So replace this by W plus minus W times V. So we have W plus V plus, because V is equal to V plus, minus W V. If we do that and take the pluses on one side, we see that this quantity, this vector, is actually equal to this vector, and that means though the in-frame rate itself is not frame indifferent, this combination is frame indifferent. This combination is frame indifferent, so we give this name, it's a rate of change, and we call it the co-rotational rate of change, and denoted by a circle on the top. So co-rotational rate of change of V is the in-frame rate minus WV. So the in-frame rate, you can measure it in any coordinate system, no matter which coordinate system you measure it in. The co-rotational rate will always take you to the same vector. Co-rotational rate will be the same vector no matter which coordinate system you use. You can do this for tensors as well, and let us say A is a frame indifferent tensor. So vectorially A plus is equal to A, and one observer sees A equal to Aij Ei and the other observer sees AAB plus EA plus EB plus, where AAB plus is QAI QBJ AIJ. This is the transformation rule that connects these two components, these two sets of components, and if this is true, then the A is frame indifferent. Now let us find the in-frame rate. What is the in-frame rate of A? For the A plus observer, the in-frame rate is, and for the A observer, O observer, the in-frame rate is, so these are the rates of change of the tensor that they see when they are sitting fixed in their own coordinate systems. So this quantity is calculated here from this transformation relation. This is how it's calculated. We replace this by omega AB, this by omega A, this by omega A omega transpose, which is equal to minus A omega. So this is the in-frame rate. So vectorially, in-frame rate in A plus is in-frame rate in O plus is equal to in-frame rate in O plus omega A minus A omega. Now again replace omega by W plus minus W, and if you do that, you will see that this quantity is frame indifferent, though the in-frame rate is not. So this we define as the co-rotational rate of second order tensor, and this is the co-rotational rate. In fact, it turns out that this is not the only frame indifferent rate for a second order tensor. There are many other frame indifferent rates, and here are some examples. So this is called the Jaumann rate. This is shown for a second for the Cauchy stress, but it can be calculated for any vector, any second order tensor, but we will use it extensively for the Cauchy stress. That's why I've written it for the Cauchy stress, but you can replace any vector A here. So this is called the Jaumann rate, and again we can show that the Jaumann rate in the O plus coordinate system is same as the Jaumann rate in the O coordinate system, just like the co-rotational rate. These are also, this is called the Truesdell rate, this is called the Green-Nagli rate, and all these rates are objective rates or frame indifferent rates, and they come in very handy when we frame constitutive equations.